Hi everybody, today we're going to be looking at logarithmic functions, and logarithmic functions have great uses in nature. One such example where we use a logarithmic function is the Richter scale to look at the size of earthquakes. And in the Richter scale we compare the variations we're getting in the ground level to a very small movement. And in some earthquakes we can be up to 100 million times a very small movement. Or in some earthquakes we can just have a very small movement compared to the original small movements. And so we have a large range that we have to try and deal with in Richter scales. And so logs can be useful because if we think about it, if we're at 10, something like 10, then we're at 1 on the Richter scale. If we're at 100 times the small movement, we're at 2. And if we're at 1,000 times small movement, then we're at 3 on the Richter scale. So here, each time we're going up by multiplying 10, so we're increasing the power of 10. So this is what we call an exponential scale, and it has a very large range. If you think, why is it an exponential scale, think, well, we're changing the exponent each time that we're multiplying by 10. Now, the Richter scale goes up by 1 each time, so we're just adding 1 each time, so it goes up in a linear way. And it's got a small range. So instead of having to do with such a large range, we can simplify it down, and the Richter scale makes it easier to work with just a small range. Okay, so that's the Richter scale, and that's how logs can be useful. So we want to look specifically at the functions. So we've developed the general shape of log of 10 of x, and it's very similar for ln of x. Well, it takes exactly the same shape. And if we have a look at the graph here, there's some things we need to notice. So the graph gets very close to the y-axis, but never actually touches the y-axis. So that means we say it's asymptotic to the y-axis. And you'll notice that the graph only exists for all the positive values of x. So it doesn't exist at y equals 0, and it doesn't exist in the negative values either. So that means that we cannot take the natural log of 0. So the y-axis represents where x is 0, and the graph does not exist there. And we can't take the natural log of a negative number. So for any negative values of x, log of that value doesn't exist. So it's really important to remember we cannot take the natural log of 0 or a negative number. So ln of 0 is undefined. Okay, another thing we could notice is that it always goes through 1, 0, and that's because ln of 1 is always equal to 0. So this point is always true for ln of x. Now it's always increasing, so if we go back to our graph and have a look at it, we notice that it's always going up as we go to the right. So it's always got positive slope, which means that the derivative will always be greater than 0 for all x in the rules. So for wherever the function exists, the derivative is greater than 0. And it's also got a very concave shape as well. So let's just remind ourselves, concave looks like that. And so, as we'll learn a little bit later, concave is when the second derivative is less than 0. So we can also say that the second derivative is less than 0 for all x in the rules. So wherever the function exists, the derivative is positive and the second derivative is negative. And then to just reiterate the point about it being asymptotic to the y-axis, our domain is just for the positive values of x, but the range is everywhere. So it takes all real values. Okay, so we want to think about, well, if we take a general form of our function, y equals k ln b, x takes c, what does each of these do? So what does k, what does b, and what does c do to change the graph? And so if we start by looking at c, you'll notice that I've kept k and b exactly the same. So k in all these cases is 2 and b is 3. But here I've gone x take 1, x take 0, so just the standard x1, and then x plus 2. And we see that it moves the graph left or right. So x take 1, it moves it 1 to the right. At x, it's just staying at the y-axis, its asymptote is still at the y-axis. Here, its vertical asymptote is at x is minus 2. So, in this case, we see that c determines the horizontal translation. In other words, it moves it left or right. So if the function is f of x is k ln b x takes c, then the vertical asymptote we can see is x equals c. Here, it's x take 1, so the vertical asymptote is 1. Here, it's x take 0, so the vertical asymptote is x equals 0, which is the y-axis. And so the domain of the function is all the values of x greater than c. So we can see for this purple one, it just exists for the values of x greater than 1. Here it's just x greater than 0, here it's x greater than minus 2. So we said that x takes c, then the vertical asymptote is at x equals c. So what about in the case when we've got a plus? How does it work there? Well, 2 ln 3 x plus 2 can be written as, well, the x plus 2 can be written as x take minus 2. And so then that means that our vertical asymptote is x equals c, so it's x equals minus 2, which we saw it was. And so the domain is x greater than c, so it's x greater than minus 2. So for the graph k ln b x, to move it c units to the right, we're going to get an x takes c in there. And then if we move it c units to the left, then we're going to have an x plus c in there. And so coming back here, we can see you moved 1 unit to the right, and we had an x take 1. Moved 2 units to the left, and we had an x plus 2. And also, if we look back at our graph, the x-intercept is affected by c, and that's something we'll revisit a little bit later. Okay, now the next part, we want to have a look at k. So we'll see that here, my value of k is changing. So outside here, it's 2. Here, there's nothing there, so in that case, it's just 1. And here, it's a half. And so we can see this is determining how far my function is from the x-axis. So this purple function, wherein it's a half, is the closest to my x-axis. The blue one, where it's 1, is further away, and then the 2 is the furthest away from the x-axis. So, the greater the value of k, the greater the modulus of the y-coordinate. So modulus is the value without considering the sign. So, in other words, this can be really thought of vertical stretching. Now, if we have a look at the points that are printed here, these are all the values at 1.2. So here, it's negative 0.916, and then for 2, it's negative 1.83. So this is doubled, going from this point to this point. And here, negative 0.916 has halved to get to negative 0.458. And if we go to these points here, we see a similar pattern. So the standard ln x, when it's 1 out the front, is it's a little hard to read, but it's 0.693 there. Now this one down here is 0.348, so it's kind of halved. And then this one, which is kind of hidden, is at about 1.8. And so that's roughly doubled. And so we can see that these points increase or decrease by the factor out the front, the factor of k. So if k is greater than 1, so we're talking about the situation where it's 2, then it's going to get further away from the x-axis. So it becomes more positive or negative. Remember, when we say the modulus, it's the value without considering the sign. So the modulus of these values has doubled, and so it's become either more positive or more negative. So the graph moves away from the x-axis, and then, as we mentioned, 0.693 doubles to 1.368, and at x equals 1.2, negative 0.916 doubles to negative 1.83. So there's this doubling factor going on. Okay, now if k is between 0 and 1, this is the half, then we see it moves towards the x-axis and each value halves. So it becomes less positive or negative. It moves closer to the x-axis. 0.693 halves to 0.347, and negative 0.916 halves to be negative 0.458. Now, also, the x-intercept remains the same, and we want to see why. So the x-intercept occurs when the function is equal to 0. So it's when k ln b x takes c equals 0. But if k was equal to 0, then the whole function would just be the 0 function. So we've got to make sure that k is not equal to 0. So the function doesn't equal 0. So k can't equal 0, so then it just must be this section that is equal to 0. That must be when our x-intercept occurs. And so then k gets removed from our equation by dividing both sides by k. And so then ln b x takes c is equal to 0. And so we can see that the x-intercept is independent of k. K doesn't have any effect on the x-intercept, which is what we saw. Okay, and finally the effect of b. What does b do? So if we look at our graph, we can see that here we've got a b value of 5, here it's a value of 1, and here it's a value of 0.4. So if it's more than 1, then it moves the whole graph up. If it's less than 1, it moves the whole graph down, or between 0 and 1. So it determines vertical translation, moving the graph up and down. So let's compare k ln b x takes c to k ln x takes c. It's done on the graphs for 5 and 0.4, but let's actually look at it in terms of the algebra. So if we've got k ln b times x takes c, we can use our log law. Our log law says that ln of a times b is ln a plus ln b. So if we apply this in the case, we get k ln b plus k ln x takes c. And actually we don't want this bracket here because that bracket's all around there to say that the k goes with both of those. So it's ln b plus ln x takes c. So then if I multiply the k out, it'll be k ln b plus k ln x takes c. So we can get this and we can see that the function, by adding b into this function, k ln x takes c, every point moves up by k ln b. And so every point on this graph, if this is just my x take point 2 ln x take point 1, every point has moved up by k ln 5. So the distance here is k ln 5, or rather I should say 2 ln 5 to make it specific to this situation. Now, why does it move down when k is less than 1, or rather b is less than 1? Well, ln of 0.4, 2 ln 0.4 is actually a negative number. And so it still adds it on, but because we're adding on a negative number, we're going to be moving down. And so this distance is 2 ln 0.4. But it's a distance down because that's negative. So if b is greater than 1, then the graph moves up to produce k ln b x takes c, moves up by k ln b. And we can see that 2 ln 5 is about 3.2. So if we look at x equals 1, then it's moved from 0 up to about 3.2. So that's what we expect it should be. And if b is between 0 and 1, then it moves down by k ln b to produce the function. Looking at that, at x equals 1, 2 ln 0.4 is about negative 1.8. And so here it's moved from 0 down to negative 1.8. And so that makes sense to us that that is moving the graph up and down by that certain amount. Now to revisit the x-intercept, well, we saw last time that it's just ln b x takes c equals 0. K doesn't have an effect. And so then if I take e of both sides, I get rid of the ln here, and I just get b x takes c is equal to e to the power of 0. E to the power of 0 is just 1. So then I just divide both sides by b, so I get x takes c equals 1 on b. And so x equals 1 on b plus c, so I add c to both sides. And so the x-intercept is only determined by b and c, and it's equal to this formula. Okay, and the last little thing we need to do is just look at what's the comparison between the exponential and the logarithmic function. So I've both graphed them on here, and if we plot some points, we can see that here, this is my point on my log function, that's 1, 0. And this is my point on my exponential function, which is 0, 1. They look very similar. Okay, well if I say this point is, say, A, then, well, actually, let's, instead of calling it A, let's just say it's some value, e to the power of A. We know that e to the power of A at some point would equal 5. And so then I can say this is ln of e to the power of A, which is just A. Okay, but here, this is my point, and I could say this is, well, A e to the power of A. And so we can see that for every point on the log function, there'll be a similar point on the exponential function that is just the reverse of the two coordinates. So for this point, e to the a, there's another point on the exponential function, e to the power of a. We saw that that occurred here. This was 1, 0, and this was the same point, just with the two coordinates reversed. So for a point xy on the exponential function, then there's a point yx on the log function. And the two functions are reflected in this line y equals x. So if you have a look, it's easy to see that this function here is just a reflection of this exponential function here. And so this implies or tells us that the log function is the inverse of the exponential function. So these two functions are just the inverses of each other. And more formally, if we wanted to show that, well, we could say y equals e to the power of x. The inverse function is just going to be that function with the x and the y's swapped, so it'll be x equals e to the power of y. And if I take ln of both sides, I get ln x equals ln e to the power of y. The ln and the e cancel, so I get y equals ln x. So if I've got some original function, y equals e to the power of x, then the inverse function is y equals ln x. And that's all the key points from today.